right. I don't know that the next speaker, I don't know that I can do the appropriate introduction really, because when we were talking, I think we became engaged because of politics. I mean, like we started, yeah, and then for seems like a couple years we've been engaging on Twitter and then having a conversation. And then I asked this year, I said, Miguel, if I ask you to attend Starship Congress, would you be okay with that? And he's like, yes, you may ask me. And so I'm like, oh my God, okay. So my excitement level came up like here, and I said, Miguel Alcubierre, would you please attend, would you consider attending and speaking at Starship Congress 2017? And when he said yes, I was like, okay, I'm a fanboy. So I'm like, Miguel Alcubierre is coming to Starship Congress 2017. And Andrea said, what? So Miguel Alcubierre, of course, wrote a paper in '94, hyperwarp drive, and introduced the concept of a working warp drive to the world. And since then, were you post-grad? PhD student when he wrote that paper, and then had fame thrust upon him. So since that time, the paper has withstood the test of time, has become we now refer to warp drives as Alcubierre drives. In fact, it's permeated pop culture so much that in Interstellar, the movie was written around it. Scott Manley, who's in the back, who plays Kerbal Space Program, one of his most popular episodes is the Kerbal Space Program video using the Alcubierre drive. This is Miguel Alcubierre. Thank you.
Thank you. Thanks. Thank you. Well, before I start, I'm just going to tell you a little bit about what I actually do for a living. You've heard about my warp drive paper, but that was only one paper written in 1994, and I haven't been back to that subject since. Okay, so just to let you know, what I really do normally, I'm not going to talk about that today, but I study black holes and gravitational waves. That's really what I do. I'm an astrophysicist, not so much as you. I'm sort of in the boundary because I do general relativity, which is not so much astros. It's a bit on the line of astrophysics. And I do gravitational waves, so this is my gravitational wave tie. If you saw the discovery of gravitational waves a year ago, this is the signal. Well, today I'm going to talk to you about how to travel faster than the speed of light. What are the possibilities? Why we think it might be possible, and why people think it's not possible as well, because that's important. So I'm going to talk about physics initially. This is the one. Yeah, so you've heard it. Everybody knows it. In principle, you cannot travel faster than the speed of light. We know that since 1905 with the special theory of relativity. Relativity is now an integral part of our understanding of the universe. It's one of the two pillars of modern physics, relativity and quantum physics. That's the whole of modern physics there. See? Light is really fast, you know that. It's so fast that in everyday life we don't really care about it. But the universe, and I don't need to tell you that here, it's really big. So if you want to get anywhere and you can't reach the speed of light, then you have a long wait. Okay. It's even a problem in our, sorry, this jumps really fast. Okay. It's even a problem in our own solar system because distances are already large enough that it takes hours for signals to get to another planet. It takes 8 minutes for the light of the sun to reach us. It takes several minutes to reach Mars when it's on the same side of the sun as we are. If it's on the other side of the sun, it takes about half an hour for a signal to reach Mars. So if you want to control curiosity, you have to tell it a long time in advance what to do because you cannot control it in real time because of the limit of the speed of light. Even worse if you go to the outer planets. So why? Why can't we travel faster than light? So I'm going to give you a crash course in relativity in the next 10 minutes, just some of the details of relativity. It's not because Einstein said so, okay? That's not how science works. It's not a principle of authority. It's because of the laws of the universe. So what is relativity? It's interesting, maybe you don't know, the idea of relativity is not Einstein, it comes from Galileo. It wasn't called exactly that, but the idea of relativity is really simple. Movement is relative, speeds are relative. You only have to say you're moving with respect to something. The first one to thought about this was Galileo. He made a thought experiment. He was thinking you're in a ship at sea, in a room with no windows, far away from the continent. And the question is, can you do any experiment in that ship that tells you if the ship is moving with respect to distant land or if it's still with respect to distant land? And the answer is you can't. There's absolutely no way to know within the ship if it's moving with respect to land, okay? That's relativity, okay? There is no absolute speed. Speed is relative. The laws of physics are independent of the speed of the observer. They are the same. So this comes from Galileo, and of course it's perfectly satisfied by Newton's physics, okay? So Newton also knew about this, and it's satisfied by Newton's physics. So what happened? What happened between Galileo and Einstein that made Einstein so important? And what happened is electromagnetism, okay? In the 19th century, we discovered the laws of electromagnetism. People like Faraday and Gauss and Ampere and Maxwell, who's there. This is Maxwell. But the problem with the laws of electromagnetism is that they seem to violate the idea that motion is relative. They seem to violate the principle of relativity of Galileo, and that was a big problem. For example, you've probably heard that a moving charge produces a magnetic field. Okay? An electric current produces a magnetic field. So if you have an electron that's moving, it produces a magnetic field. But who decides if it's moving? I told you motion is relative. So if I move with the electron, then the electron is at rest with respect to me, so there shouldn't be a magnetic field. So question, is there a magnetic field or isn't there? So that's a problem. Okay? The magnetic force on a particle depends on its speed. Who measures that speed? The speed of electromagnetic waves is actually the speed of light, because light is an electromagnetic wave. We usually call it c. It comes out of the equations independently of any reference frame. So again, who measures that speed? With respect to whom it's supposed to be measured. All those things worried physicists at the end of the 19th century. These things apparently violated the relativity of motion. And people like Poincaré and Lorentz were really worried and were really thinking about these things in the last decade of the 19th century, and were trying to find a way to understand this. They even invented something we call the ether that now we don't believe. And even worse, experiments showed that the speed of light in the laboratory was completely independent of the motion of the Earth. Now, the Earth moves very slow compared to light, that's true, but you can measure it. Okay? The apparatus at the end of the 19th century were already good enough that you should be able to measure the effect on the speed of light due to the rotation of the Earth around the sun. And they couldn't measure anything. It came out zero. That didn't make any sense. So that's why Einstein is important. Einstein appeared in 1905. By the way, this is the Einstein of 1905. It's not the old guy you all remember. It's the young guy. He was 26. Okay? And he tried to reconcile Galileo's principle of relativity with electromagnetism. Actually, his paper on relativity is called On the Electrodynamics of Moving Objects. Okay? It's a paper about electromagnetism. And he says, okay, let's assume that Galileo is right. Motion is relative. The laws of physics are absolute, independent of the speed of observers. But let's assume something else, that the speed of light is also absolute. This is strange. It sounds contradictory, because this principle, number one, tells you speeds are relative. Number two tells you, wait, one speed is absolute. Okay? It seems that it doesn't make any sense. It actually does. He figured out that there is one mathematical solution that allows for that. You can have one, you can say all speeds are relative except one. That works. And that one is the speed of light. So he did the math, and out came relativity. All relativity theory came out of those two postulates. So modern theory of relativity is a theory that tells you speeds are relative, but there's one that isn't. The speed of light is not relative. It's always the same. It doesn't matter how you measure it. The speed of light is the same independently of the speed of the source of light, independently of the speed of the observer who measures the speed of light. It's the same number always, which doesn't make any sense. Because if you take Newtonian physics, you can show that speeds add up. You can add speeds, okay? They're additive. But the speed of light is always the same, tells you that you cannot, if you add anything to the speed of light, it remains always the same. So something is wrong. They don't add up. So, and in Newtonian theory, you show that they add up just because of your definition of space and time. So if they should be additive by your definition of space and time, and there's one speed that violates that, there's only one possible conclusion. Your definition of space and time is wrong. What you thought of space and time is wrong. You need to rethink space and time, okay? So that's the whole content of the theory of relativity. Space-time are not what Newton thought. Space and time are something different. So that's how it gets born. Yeah? Now, there's a lot of interesting things Einstein showed really quickly. Now, that's one other thing before I go there. It's called the theory of relativity, right? But it's based on two things that are not relative. It says the laws of physics are absolute. The speed of light is absolute. Why do we call it the theory of relativity if it's based on two things that are actually absolute? Well, we call it the theory of relativity because other things come out to be relative. The price you pay for taking the speed of light to be absolute is that other things we thought were absolute are actually relative. Flow of time is relative. You have time dilation. Distances are relative. You have contraction of distances when you move very fast. Simultaneity is relative. This is crucial. I'm going to come back to that one. Mass and energy are equivalent. That also comes out of it. That actually came in the second paper, the famous equation E equals mc squared. And of course, nothing can travel faster than the speed of light. This all comes out of relativity, okay? All of modern physics is based on special relativity. All of modern physics. If you violate special relativity, the whole building of modern physics collapses, okay? So, and we've checked this and rechecked it, and we've done thousands and thousands of experiments in the last 100 years, and it's never failed, okay? So it's not just a theory, okay? We've checked and rechecked. Now, in 1908, something interesting happened. This guy here, Minkowski, who was a mathematician, he was actually Einstein's teacher at the university, discovered something really crucial. This is a quote from him, from his paper. He says, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. And what he meant is something that I put the equation there, don't worry too much about it. But what he discovered is that Einstein's special relativity could be recast as a theory of geometry, but a theory of geometry in 4 dimensions, not in 3. 4 dimensions being the 3 spatial dimensions we know, and time. Time is the 4th dimension. And he discovered that everything that Einstein had proven could be understood by thinking that in 4-dimensional space-time, there was a measure of distance that was absolute. Okay? So if you remember Pythagoras' theorem, so the square of the sides of the triangle is equal to the square of the hypotenuse. Well, it works also in 3D. In 3D, you can have the distance between any 2 points in 3D. You can decompose it in the distances in 3 dimensions squared, and then that gives you the total distance squared. Well, it also works in 4 dimensions, except that there's a weird, funny sign here. The 4th dimension comes with a minus, which is a very strange form of the Pythagoras theorem, plus, 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 minus. But that gives you a measure of distance in 4 dimensions, and it's absolute. It's absolute. Everyone will measure the same thing. It doesn't matter how fast you move. It doesn't matter what you do. It always comes to the same number. There is a measure of distance in space and time that is absolute. Okay? We call it the interval, or the line element, or many other names. We don't like to call it distance because of this minus, these worries. This is French, okay? But it works. So there's geometry in 4 dimensions. Space is relative, time is relative, but space-time is not relative. Space-time is absolute. Space-time has an absolute distance. This is the great discovery of Minkowski in 1908. And everything Einstein said before can be shown to come from this. Okay? This is the basis of special relativity. So special relativity is a theory of space-time in which you have a distance in space-time that works sort of like the Pythagoras theorem with a minus in here, okay? So this is the great discovery. Initially, Einstein didn't like this. Einstein thought this was very abstract. And he thought Minkowski is crazy. What he's saying is probably true, but it's very abstract. Then he changed his mind, okay, quickly. Now, what does this imply? This implies that there's something very important in space-time. This minus is crucial. It tells you that in space-time, there's an absolute structure. And that absolute structure actually has to do with causality, okay? Causality is the fundamental property of space and time. And this can be illustrated by something we call the light cone. Imagine you have an event here. Something explodes, for example, a big supernova explosion. Then you make a diagram in space and time, time goes up, space goes like this. And then you plot in this diagram light rays. Light rays move, for example, to the right and to the future, and they move along this trajectory, and to the other side, and backwards in time. And this gives you a cone, okay? A cone to the future. We call that the light cone. The light cone is all those events that can be reached from a given event at the speed of light, okay, to the future or to the past, okay? That's called the light cone. And since everything that travels slower than light moves inside the light cone, this is light. And if you want to move outside the light cone, you have to travel faster than light, okay? Since the speed of light is absolute, the light cone is also absolute. Every observer, no matter how fast he moves, has the same, will agree with the light cone. Okay? It's always the same one. Oh, sorry, this just jumps really fast. Okay. Now, another thing you find is that observers that move with respect to each other do not agree on which events happen at the same time. As I mentioned before, simultaneity is relative. If I say two things happen, one over there, and they happen exactly at 12 o'clock, somebody that's moving with respect to me very fast will say that's not true. One happened before, the other one happened after. And somebody moving in the opposite direction will see them the other way around, which is really nice, okay? Simultaneity is not absolute. We cannot agree on things that happen exactly at the same time. That's one consequence of relativity. Okay? But they always agree on the light cone. Now, this is a problem. This is a problem, okay? So, as I mentioned here, imagine two events, one here, the explosion, and another event in the future. Say somebody explodes over there, there's a brick flying in my direction, and it hits me here and it kills me, okay? So this is clearly the consequence of that. It exploded, it killed me. Yes? There's cause and effect. I know that A happened before B, okay? And so everybody has to agree that A happened before B. If they move very fast, they have to agree, okay? But what happens if I have events like here, A and B? They happened exactly at the same time. A and B happened at the same time, simultaneous, okay? Somebody that moves with respect to me will say, no, that's not true. A happened before B. And somebody that moves in the other way will say, that's not true. B happened before A. Now, this is complicated because if he thinks A happened before B, he might be able to say, well, then A might cause B. Okay? But this guy saw it the other way around. He said, no, A can't cause B because B happened before A. So it doesn't work, okay? So if you don't agree in simultaneity, then you have a serious problem. You might break causality. If you can't agree in the order of events in time, which one happened before, there's a risk of destroying causality. There's only one way out. The way out is to say that nothing can travel faster than light. You use the light cone. The light cone is the only thing that's absolute. So you say causality is always contained within the light cone. Okay? This is the solution. The light cone defines causality. Different observers do not agree on the time order of events that are outside the light cone, but they always agree on the order of events inside the light cone because the light cone is absolute. And as a consequence, if any object would travel faster than light, that is outside the light cone, then it would violate causality. Because if I moved from here to here faster than light, then there's some very reasonable observer that would actually see me arrive before I ever left, which makes no sense. It destroys causality, okay? Traveling faster than light destroys causality. Traveling faster than light allows us to travel back in time, which makes no sense. So that's why we can't do it, okay? Faster than light travel violates causality. Faster than light travel would allow you to travel back into the past, which is why it's forbidden. It's not because Einstein said so. It's not because we don't have the technology. It's because it destroys causality. And we don't like causality being destroyed. Okay? But we haven't even seen it. Nothing has ever traveled faster than light in our universe as far as we can see. There's no experiment that has shown anything traveling faster than light. It seems to work. This seems to really represent our universe, okay? So that explains why, okay? It's not because Einstein said so. It's not a problem with technology. It's not a problem with ideas. No, it's a problem in the way our universe is built, okay? So we can always travel faster than sound. People said, well, you couldn't travel faster than sound, and you can, but that was just a technological problem. Things have traveled faster than sound forever. We've been able to move objects faster than sound for at least 500 years. They're called bullets. Okay? They travel faster than sound. The problem was to build an airplane. That's an engineering problem. We cannot travel faster than light, not because of an engineering problem. It's because of the way the universe is built. Okay? It's because of the basic properties of the structure of the universe. It's because of Minkowski's distance. Yeah. So that was the situation, and if that's it, then I would finish the talk here. But of course not. I'm going to go ahead. Something else happened in 1915. A second huge contribution by Einstein. Einstein deserved at least 3 Nobel Prizes, I think. He only got 1. And he only got it for something that has nothing to do with relativity. It comes from quantum theory. But in 1915, he did something else. He actually discovered it really early on. We have a theory of gravity. We already had a theory of gravity since Newton, universal gravitation, which works pretty well. Okay? We still use Newton's theory to send probes to Mars and Jupiter. We don't need relativity. We do it with Newton's theory. But there was a big problem with Newton's theory. According to Newton's theory, the speed of gravity is infinite. Gravity is instantaneous. The speed is infinite, okay? That's a problem. That was even a problem in Newton's time. People complained about that to Newton. They told him this action at a distance doesn't make any sense. And he said, I know it doesn't make any sense. If you have a better idea, tell me. And of course, nobody did. Nobody had a better idea for 300 years, but he knew it was a problem. But it became a serious problem with Einstein, because if gravity travels at an infinite speed, it violates relativity. I just told you nothing travels faster than light, not even gravity. So if gravity travels faster than light, then it's wrong. Newton's theory of gravity is wrong. So Einstein dedicated the next 10 years of his life to find a new theory of gravity that would not violate relativity. It turned out to be an extremely complicated theory. It took much longer than he thought, but he eventually found it. He was guided by a nice thing, and I'm going to divert myself a little bit here. I'm going to take some time. He used a very beautiful idea that also comes back to Galileo. It's called the principle of equivalence. He actually called it, at one point, the happiest thought of his life, Einstein, the best idea he ever had. It's called the principle of equivalence. And the observation of Galileo is that if you have gravity and you let objects fall, they always fall with the same acceleration. Go to the roof of the building and you throw a little pebble and a big ball of metal, they fall at the same rate. It's not true that the heaviest one falls faster. They fall at the same rate. This was discovered by Galileo. But Einstein turned it around. Einstein said, okay, this is the key property of gravity. And he postulated like this: the laws of physics in free fall, when you let yourself fall, are identical to those in the absence of gravity. If you let yourself fall, gravity disappears. So this is Einstein's contribution. It comes from an observation of Galileo. And he used that to build his theory. It took him still another 8 years, as you can see. But, and this is, by the way, the reason why astronauts float in space. If they ask you, why do astronauts float in space, and you answer because there's no gravity there, you're wrong. There is gravity there. The International Space Station is only about 400 kilometers up, which is nothing compared to the size of the planet. So of course there is gravity there. It's about 95% as intense as here. It's almost the same as here, but they float. Why do they float? You know the answer? They're falling, exactly. They float because they're falling. They're falling around the Earth all the time. They're always falling. And if you fall, then there's no gravity. Okay? So you float because of the principle of equivalence. You can also do it on Earth. You don't have to go to space. You can go in these beautiful planes that go up in a parabola and then let themselves fall down in free fall. And then you float. The difference is if you go to space, you can float for months. And if you do it in an airplane, you can only do it for about 30 seconds before you crash into the ground. So, but you can do it. This is called parabolic flight. This is how they train astronauts. And I was lucky enough, thanks to a few friends, one of them who's sitting way up there, Juan Jose, who were crazy enough to take us to Russia on one of these planes. This is a movie. Can you click it? Can someone click the play? That's me. You can see us float. That's another friend of ours. There's another friend. Juan Jose was somewhere in the back. He's not in this take, but he was there in the same flight, on the same plane. So I show it to you because I think this is the closest I'll ever get to space myself. But okay, this is the principle of equivalence. If you let yourself fall, gravity disappears, okay? Einstein took this idea and he used it to build a new theory of gravity. This new theory of gravity is called general relativity. And what he discovered is that he could use this idea of Minkowski, that relativity was geometry, but he needed to change the geometry. So he needed to make space-time curved. Okay? So basically that comes from the principle of equivalence. I'm not going to get into any detail, but the theory of general relativity, it's called general relativity because it takes the theory of relativity of Minkowski and his space-time, and it generalizes it to a curved space-time. That's why it's called general relativity. In my view, it's not a very good name, because it's actually a theory of gravity, and it doesn't say so anywhere in the name. But that's the historical name, okay? But that's the reason, okay? Generalizes special relativity to curved space-time, and that curvature is gravity, okay? So general relativity is a new theory of gravity that combines special relativity and the principle of equivalence, and it postulates that gravity is a distortion in the geometry of space-time, a curvature in space-time, okay? That's the reason of the name. So from general relativity, we get black holes, we get gravitational waves, we get the Big Bang Theory, we get all of modern physics in space, okay? All of modern astrophysics comes from general relativity. It is our theory of gravity today. Even if we still use Newtonian theory because it's easier when we don't need the full-fledged theory of gravity, the theory of gravity we have today is general relativity. These are the equations of general relativity. I'll show them to you in a minute. They're written here nicely in an old train somewhere in Argentina. No, sorry, somewhere in Bolivia, sorry. There's this old train rusting out, and somebody went there and wrote Einstein's equations on that. So in the words of a famous physicist who died about 10 years ago, a bit less, John Wheeler, space-time tells matter how to move, and matter tells space-time how to curve. Those are the equations of Einstein. These are the equations again. These are Einstein's equations. When a physicist thinks of Einstein's equations, we think of this, okay? E equals mc squared is not Einstein's equations. It's just a simple relation. These are Einstein's equations, the equations that tell us how space curves, okay? It doesn't matter if you don't understand them. All I'm going to say about them is that the right-hand side, this T, we call it the stress-energy tensor. It represents the distribution of mass and energy in the universe or in space. The left-hand side, this G, we call it Einstein's tensor, Einstein's curvature tensor, and it represents the geometry of space-time, okay? So geometry equals distribution of matter and energy. Okay? The equations are really beautiful. Actually, these are more complex than you need. You can cross out this term. This term is a cosmological constant. It's only important for cosmology. So if you're thinking about just black holes and things like that, this is zero, okay? These are the equations. But I'm going to talk about those equations in a minute, okay? So a little bit about them. So they're extremely complicated equations. For those of you who understand a little bit of mathematics, there are partial differential equations, second-order partial differential equations in 4 dimensions, coupled and nonlinear. Worse, they have thousands of terms. They look very innocent. But actually, when you write them out completely with every single term, they have literally, I'm not exaggerating, about 3,000 terms. You just put them in Mathematica or Maple and expand them, it's about 3,000 terms. It's true. So they're complicated, okay? They're difficult to solve. How do we solve them? How do we normally solve them if we are doing astrophysics, if we want to study the origin of the universe, if we want to study black holes, anything like that? What we do is this. We give a reasonable distribution of matter at energy. We say there's a star there, or there's a galaxy, or there's a black hole. Or we have the whole universe with matter distributed such and such. So we give a reasonable mass-energy distribution. We plug that into the equation, solve the differential equations, which are really complicated, and obtain out a physical space-time geometry, the geometry of space and time. This is the way we do it normally. That's the way we get astrophysical relevant solutions, okay? Give energy and distribution, mass and energy, obtain geometry. But the thing is, you can do it the other way around. And that's where I'm going to come back to that in a second. You can cheat, okay? So you can go back and say, no, I'm going to give you a nice space-time geometry that I like for some reason. I like the geometry. So I put it here, work from left to right, and read out the mass-energy distribution I need, okay? That's called design your spacetimes. You design your spacetime the way you like it, and read out the energy distribution. Most of the time, this makes no sense. It's nonsensical, okay? When you work this way, you say you solved Einstein's equations. When you work this way, you say you just gave a model for a nice geometry. This is not a solution of Einstein's equations. This is, okay? And that's important because the rest of the talk, I'm going to go this way. Now, once you've accepted the fact that you can change the geometry of space and time, then you can use that to cheat Einstein. So you can use Einstein to cheat Einstein. You can use that to figure out geometries that allow you to travel faster than light. And that's a nice thing. The easiest thing to imagine that the first people thought of is you can make a tunnel. Imagine you live here, this is Earth, and you want to go to a distant galaxy which is over here. So if you could bend space and then make a tunnel, if you go this way, it might take you thousands of years, but if you go this way, it might take you just an hour, okay? This is easy. You can draw the geometry really easy. That's it. I just drew it, okay? This is called a wormhole. It's also called an Einstein-Rosen bridge. Why? Because Einstein and Rosen were the first ones to figure out a geometry like this in the 1930s. So even Einstein himself already knew about this, okay? This is a wormhole. We've known about these things for 80 years or more. But this is a simple geometry. Now, are they allowed in general relativity? Actually, yes, they are allowed in general relativity. The very first solution of the equations of Einstein was found in 1916 by Carl Schwarzschild. This is interesting because when Einstein first presented his equations in November 1915, they were so horribly complicated. They are very complicated. But Einstein saw them and he thought, these things are so horribly complicated that nobody will ever find a solution. So I'm going to work on finding approximations. And that's what he did. But 2 months later, Carl Schwarzschild in February 1916 discovered a true exact solution. So Einstein was wrong. You could actually find solutions. The first one was discovered in 1916. This solution now we know represents a black hole. At the time they didn't understand it very well, but it represents a black hole. And it turns out to have not only a black hole, but a wormhole inside. Now, black holes and wormholes are different things, okay? A wormhole is this tunnel, and a black hole is this thing you get at the end of the life of a large star when matter has collapsed itself to a point. So they're different things. But inside a black hole, you have a wormhole, which is weird and nice. This wormhole inside the solution is so complicated that nobody could figure it out completely. And it took 20 years before Einstein and Rosen discovered that inside that solution there was a wormhole. Okay? They called it a tunnel, and because of that, they're called today Einstein-Rosen tunnels. So it's there in the solution. It's a mathematical solution. But this wormhole is not very useful. It's actually not useful at all. This wormhole inside a black hole is dynamic. It means it closes up. It opens and closes. It closes up so fast that it makes it impossible to traverse it. Even if you're going at the speed of light, it will just collapse on you. And they connect to a different universe. So even if you could go through, you'll end up in a different universe, not in another part of our universe, which is not particularly interesting, okay? But it's been used in science fiction, as you know. Carl Sagan used it in his novel Contact. He actually contacted Kip Thorne, who's a friend of mine, to ask him about these things. Carl Sagan wanted to use a black hole in his novel to travel to other stars, and Kip Thorne told him black holes don't work, would use a wormhole, and that worked. So it's been all over the place in science fiction. There's another. This is Stargate, so they have wormholes. This is Deep Space Nine, Star Trek Deep Space Nine, they have wormholes. It's all over the place in science fiction. So remember, they are allowed by the theory of relativity, okay? We don't know how to make them, but they are allowed. But there's another idea, which is the reason I'm here. There's actually more ideas, but I'm just going to mention this one, okay? Back in 1994, I had a different idea. I was watching Star Trek, which is true, and it got me to thinking, if there was any way in which you could come up with a geometry of space-time that was similar to this idea of warp drive in science fiction, that allowed you to travel faster than light, bending somehow space. Okay? So my idea was not to move through space, but rather to move with space, somewhat similar to what you do in travelators at airports. They just stand there and you move. You don't have to walk. It just pushes you along. So the idea was if space can do the work. And I came up with the concept of what I call today a warp bubble. I don't like the name warp drive, even though I use it, because drive gives you the idea that there's a machine, okay? Gives you the idea that there's a ship. I don't know anything about a ship. I have no idea how to make it work, so I prefer to call it a warp bubble. Okay? It's a distortion in the geometry of space and time. So the idea is if you're sitting in a region of flat space-time, and somehow you can expand space behind you really violently, that will, if I expand space here, it will move me away from the wall. And if I contract space in front of me, it will move me towards that wall. So if I can do that, if I can expand space here and contract it here, I'll move that way without having to move at all. Okay? That's a basic idea. It's similar, as I was saying, to a travelator in an airport. If you're going in this traveling dance in an airport, you can imagine that behind you, the floor is being created out of nothing. Of course, it's not, but you can imagine it. And in front of you, floor is being destroyed. And then you move along, right? So that's the idea. You have space being created, expanded behind you, space being contracted in front of you, okay? And you sit in an ice region in the middle where nothing is happening, in a flat region. So that's the basic idea of the warp drive, or the warp bubble. Local expansion of space behind you and a local contraction in front. This idea is similar to the idea that we know of the expansion of the universe. We've known since the 20s that the universe is expanding, okay? The universe does expand, so space-time can expand. When you think about the expansion of the universe, many people think it wrongly, because when you hear the Big Bang, you think something exploded and things just flew off in every direction. That's not the Big Bang, okay? That's not how it works. When people ask you, where was the Big Bang? Well, it was here, it was there, it was everywhere. The Big Bang is not an explosion in that sense. The Big Bang is the creation of space that wasn't there. We didn't have anything, and then suddenly space appeared and it started stretching. It's much more similar to the idea if you have one of these rubber surfaces where kids like to jump, but it's really long and infinite, and you start pulling it from the sides. So then it will expand, okay? But everywhere at the same time. So that's the expansion of the universe. Space is expanding, so we know that. So, of course, it's allowed to expand in the same way it's allowed to contract. Okay? And there's no limit to how fast space can expand. It can expand faster than light. That's OK. There's no problem. That doesn't violate anything. It doesn't violate anything in relativity. Space can expand at any speed. In fact, that's true today. If you go far away into the universe, you probably know the expansion of the universe implies that galaxies that are further away from us move faster and faster away from us. OK? The further away a galaxy is, the faster it moves. The first question that comes into mind, is it possible for a galaxy to be so far away that it's moving with respect to us faster than light? Yes. We call that the cosmic horizon. That's a place where galaxies are moving so far away, so fast away from us that they're actually moving faster than light. Does that violate relativity? No. That's actually a consequence of relativity that comes out of the theory of relativity. So yes, galaxies can move far away from us faster than light, yes. Why? Because they're not actually moving. They're actually at rest. What's moving is space. Space in the middle is expanding. And space can expand at any speed it wants. That's not a problem. Okay? So that's the idea of the warp drive. Okay? If you want to see the mathematics, I just put it there. It's pretty simple. that's actually the warp right there. Right there. It's a geometry of space-time. Remember Minkowski? The Pythagoras theorem, so this is the two pluses and one minus. And on the other direction, the direction you want to move, you change it. It doesn't really matter, the details, but you have to change it in one direction. But it's a geometry. What I wanted you to see is that it's a simple equation that represents essentially Pythagoras theorem in 4 dimensions. It's just geometry. That's all it is. So that's my paper right there. My paper is just writing this equation, explaining the terms, and telling people what it means. That's the whole paper, okay? It's really simple. I'm not going to go into the details, but I just wanted for physicists in the audience, that's it, okay? That's the paper. Now, there's problems with the warp drive and with the wormholes. There's several problems. Now, as I said before, when you solve Einstein's equations, a real, true, bona fide astrophysical solutions of Einstein's equations is tell me the matter distribution, I will work through the differential equations and solve for the geometry of spacetime. That's the way to do it. This is the other way. This is, I want this geometry, I like it, it's nice. Plug it into Einstein's equations, see what mass energy distribution you need. And what happens is that mass energy distribution usually is nonsensical. Doesn't make any sense. The first thing you discover when you plug that and do that for the warp drive and also for wormholes is that you need something that physicists call negative energy, okay? First you need a lot, yeah? And then you need something that's called negative energy. Now negative energy, maybe it doesn't sound extremely strange to you, but remember, energy and mass are the same thing. E equals mc squared. Mass and energy are the same thing. So when I say negative energy, I really mean negative mass. Negative mass, that's a problem. Have you ever encountered something that weighs minus some number of pounds? No, right? There's no negative mass. There's no negative energy as far as we understand. It has never been found in nature. No known form of energy produces this. It's another way to say we need antigravity, okay? Negative mass would produce antigravity. We've never seen antigravity in the lab. We don't know of any kind of energy distribution that produces antigravity, not even theoretically. Nothing. It hasn't been found in any accelerator, okay? There are some quantum effects that might, but that's another story. If you have a question, I might answer it, but they're extremely tiny. But it's, on the other hand, we've never found it, we've never seen it, but it's not forbidden. There's no law in physics that says this can't happen as far as we understand. So that's a problem, okay? It happens both in the case of the warp drive, and it happens also in the case of wormholes. Not only that, you need negative energy, and you need huge quantities of it. The original version of the warp drive, the one I showed you here, I never did the calculation myself, but somebody did it a few years after. If you wanted a warp bubble about 100 meters in diameter, with walls of about 10 meters where this expansion and contraction are happening, and you calculate how much negative energy you need, it turns out that you need the equivalent in negative energy to the mass of the entire universe. So you need negative energy, and you need a whole universe of it, which is ridiculous. Okay? Then people played with this and modified it and made some assumptions, and eventually someone published a paper in which he showed mathematically that you could find a modified version of the warp drive that would need about the mass of Jupiter in negative energy to push a spaceship not bigger than a car, okay? Imagine a spaceship the size of a car. You want to move that about twice the speed of light. You will need the equivalent of the entire mass of Jupiter in negative energy to power it up. So you need negative energy, and you need ridiculous amounts of negative energy. That's really a big problem, okay? Another interesting thing that I just added this slide yesterday because people keep asking about it. People tend to think that because space is expanding behind me in this warp bubble, that means that the negative energy has to be behind me because it's anti-gravity and it produces this. But that's not true. When you do the math, it turns out that the negative energy is actually located to the sides around you in a torus. Right? It's not behind you. It's not in front of you. It's around the sides. That's where you need it. This is a plot of the negative energy distribution in a warp drive with thick walls and with thin walls. And the warp drive is actually moving to the left, to the right, sorry, left to right. You see that the negative energy is towards the sides, okay? It's in the sides. That's interesting. And that explains these. You've probably seen these, right? This is a nice concept warp drive spaceship designed by Mark Radmacher. So why did he put these strange lobes here? Because he knows that if you want negative energy, it's around you. So you need to have something that generates negative energy around you, not on the back, okay? And that's the reason he put this in the design. Now, please don't fall for the hype. This is a nice concept based just on the metric, but we have no idea how to build this at all. We have no idea how to build a warp engine. We don't have the negative energy. And even if we did, we would need an entire planet, okay, of negative energy. So that's not practical, okay? Now, another question. Does negative energy actually exist? As I said, we have never seen it, but that's not entirely true. Until this number should probably change now to about 20 years, but until about 20 years ago, we have never found any evidence of anti-gravity in the universe, but 20 years ago, something strange happened. People were studying the expansion of the universe, and particularly they wanted to find out if the expansion of the universe is slowing down and how fast. We call that the deceleration of the expansion, how it decelerates. If I throw this up, it will eventually come back down. So it decelerates and then comes back down. So the same idea applies to the universe. If it's expanding, it will slow down and maybe eventually come back out. So they wanted to measure how fast it's slowing down. And for that, they needed to measure the distance to very far supernovas and very detailed and very carefully, the distance to a lot of supernovas really far away. So it took them many years. It was people were only able to do it in the 90s because the technology just wasn't there before. Eventually, they measured it, and big surprise, the expansion is not slowing down, it's accelerating. This is just as terrible as if I just threw this up and I saw it accelerate upwards instead of falling back down. It's exactly the same thing, just on the scale of the universe. It doesn't make sense. Okay? So the people that did this work initially thought they were wrong and decided not to publish it and start again from scratch. And they did it again. It took another 2 years, and they got the same result again. So they decided to publish it. Eventually, they got the Nobel Prize for that. But initially, it was really scary. The expansion of the universe is accelerating. The only way we can understand that today is if at the cosmological level, there is something that produces anti-gravity. We call it dark energy. We don't know what it is. Dark energy is just the name for something that we don't know what it is, but that constitutes 70% of the total energy content of the universe and produces anti-gravity. So there is a hint of anti-gravity in the universe out there. Can we use it to create wormholes or warp drives? We don't know. It's still too early to know. Maybe not. Hopefully, yes, but who knows? You can hope that maybe this will save the day. That's my hope. Okay. Now, there's another problem with the warp drive, which normally I don't talk about, but there's an interesting problem. It's called the horizon problem. Turns out that if you want a warp drive that moves at speeds that are small, you don't need a warp drive to move faster than light. You could use it to move slower than light. If you want that, you need negative energy, and that's a problem. But if you want to use it to move faster than light, then there's another problem. It turns out that this is the warp bubble again. This is the spaceship here. Space is expanding in back and contracting in the front, okay? If it's moving faster than light, it turns out there's a region in front of the bubble that is completely causally disconnected from the ship. It means the ship can't send the signal here. It means the ship can't put the negative energy there even if it has it. It can't reach. It can't stop it. It can't do anything. It's this region in front of the bubble. It's completely out of touch with the ship, which means the ship cannot control it. It cannot even start it. You cannot reach the front, which means you can't do it. Okay? You cannot do it from inside the ship. You would be able to do it from the outside. You could say somebody went there, slower than light, with a normal rocket, and put negative energy mass generators along the way, and then somebody came behind it, and these generators were just switched on at the right time as this other ship was passing by, and then you could do it. But you cannot generate the warp bubble from the inside if you want it to travel faster than light. It has to be set up from the outside. That's called the horizon problem, okay? It's a very serious problem. As far as I know, nobody's been able to solve this one, okay? And of course, as I mentioned at the beginning of the talk, why we can't move faster than light? Because it breaks causality, okay? It turns out it's still true. If you find any way to travel faster than light, even cheating with wormholes or warp bubbles, anyway, you still can use it to build a time machine. You can use it to travel back in time. And this is not nice. You might think it's nice if you like science fiction. But from the point of view of a physicist, it's not nice, it's horrible. time travel destroys causality and brings with it many paradoxes. I'm sure you've seen them if you like science fiction, the grandfather paradox. Travel to the past and kill a young boy who was supposed to be my grandfather. So if he's dead, how is he my grandfather? And he's dead, how was I born? And then if I was not born, how did I go back and kill him? It doesn't make any sense, okay? I like this one, Where's the Watchmaker? I like that one. You've seen it probably in a movie, an old movie from the 80s, Time After Time, I think it was called, or something like that. It's an old man gives me a nice watch. So I'm giving this talk, and then it's a nice old guy from there. He comes here, says, I like your talk. I want to give you a present. He gives me a nice watch and said, oh, nice. Take the watch. Later I invented a time machine. I traveled to the past, about 80 years to the past. I meet a young boy, 5 years old. He likes the watch. I give it to him. And this little guy eventually grows up to be the old man that gave me the watch. It's the same watch. Who built it? Who made the watch? It was never made in any factory. It's just been going around. Nobody ever created the watch. Doesn't make sense, okay? It's worse. You can do, because people say, well, the watch will eventually break down. It's just going round and round, it'll break down. Right? But you can do it with something that's not physical, that's information. I travel to the past and meet an old and half deaf and very depressed Beethoven, who's only wrote 8 symphonies. And he doesn't want to write anything else anymore. So I just try to cheer him up, and I sing the Ode to Joy to him. And he likes it, and he writes the 9th Symphony. So who composed it? It wasn't me, because I heard it in a CD of Beethoven's music, and it wasn't him because he heard it from me. So there's a loop of information. Who invented that? That doesn't make sense. So time travel is nasty, okay? We don't like it. We don't like it at all. That's the reason why Stephen Hawking actually has a conjecture. He calls it the chronology protection conjecture, which is complicated language just to say that the laws of physics prohibit time travel to the past, okay? That's what it says. It's a conjecture, which means it has not been proven, but there are actually very good arguments in its favor based on quantum physics, yeah? But it doesn't actually prohibit faster than light travel. It only tells you that you cannot use it to build a time machine, okay? Which is nice, I like that. Because if this is true, then we might be able to travel faster than light as long as we don't try to use it to build a time machine. If you try to use it to build a time machine, something's gonna go really bad. What could happen? Your time machine collapses into a black hole before you can use it, for example, or it explodes in your face. And that would make sense. But I like this, okay? That gives me hope. But finally, and I'm gonna go back to the talk by David Brin, do we really need to travel faster than light? Well, we need to travel faster than light if we want to go back there and come back as ourselves in our lifetimes, okay? But we forget about that. If we think just about the species, humanity, then we don't really need to travel faster than light, okay? Traveling at 10% of the speed of light, you can cross the entire galaxy side to side in 1 million years. 1 million years is a long time for a single individual, but it's not a long time at all for the human species, okay? You could actually colonize it to the very last star in less than about 5 million years. Actually, David Brin said 3 million. So in less than about 5 million years, you could colonize every single star in the galaxy if you could travel at 10% of the speed of light. And 10% of the speed of light doesn't seem unreasonable at all. It seems pretty feasible. Okay? There's nothing preventing us from doing that. Okay? We could probably have a spaceship doing that if you commit the resources in about 100, maybe less than 100 years, in a few decades. If we really had the financial resources and the will to do it, we could probably do it. And we could colonize the entire galaxy to the last single star in a few million years. So that brings me back to the question of the Fermi paradox. Where is everybody? Because if we could do it in 5 million years, why nobody has done it? The galaxy is 12 billion years old. So nobody's done it in those 12 billion years? Nobody's had the idea to do it? If a single species had decided to do it, the galaxy would have been overrun a long time ago. And it hasn't been. So that really worries me. That keeps me up at night. Where is everyone? We're really alone? So that's worrying me, okay? So with that, I essentially finish the talk. Can we travel faster than light? So special relativity tells us no, because it would break causality. General relativity seems to allow us to cheat, but it requires antigravity, negative energy. and huge quantities of it, planetary-sized quantities of it. And even if we could, at least in the case of the warp drive, we would also need to solve the horizon problem, which nobody knows how to solve. If you have a wormhole, that's not a problem, but nobody knows how to make wormholes anyway. And even if it turns out to be possible, with all these ifs, we still need to face the problem of time travel paradoxes, which is really a problem. So I don't really know the answer. Okay? I think at least what has changed perhaps in the last 30 years or 20-something years is that 20-something years ago we would have said, it's impossible, forget about it. Today we think, maybe there are some ways in which you could get around the laws of physics and do it, but it's still highly, highly speculative. Okay? So I'll leave you with that point. Thank you very much.
Questions?
Yes.
What if we would be happy just going forward in time? How do we do that?
Forward in time we can. We can travel forward in time. That's not a problem. The easiest way to say it is we're traveling forward in time now, 1 second at a time. But you want to go faster. You can do that as well. There's two ways to do it. You can go very, very fast, very close to the speed of light, far away and back. And then you use something called the time dilation. It turns out that when something moves very fast with respect to you, its clocks slow down. So if you could move, say, to Alpha Centauri at 99% of the speed of light and back, then on Earth, Alpha Centauri is 5 light years away, so on Earth it would have been about 10 years. And for somebody on that spaceship, it could have been a month. So that's a way to travel forward in time. You experience 1 month, and you actually went ahead in time 10 years. You can do that. Another way to do it is to use another phenomenon called gravitational time dilation. That's also been proven. We know that gravity causes time to slow down. That's also proven. It's been measured without any doubt. Actually, you measure it every day. You just don't know. Whenever you use this thing to locate your position, GPS proves time dilation every single day because gravity slows down time, which means time here on Earth goes a little bit slower than time up there where the satellites, the GPS satellites, are going around. So we lose 1 second every 30 years because of the gravity on Earth. But that doesn't seem like a lot, but it's perfectly measurable. You can measure it with atomic clocks, and the GPS satellites are essentially atomic clocks. So if you don't take it into account, the GPS doesn't work. You have to take it into account because GPS is based on having perfectly synchronous atomic clocks in orbit. And if they're gaining 1 second every 30 years, that means they're in distance, that would mean they would be wrong by about 100 meters every week, which is a disaster for the GPS. So you measure it every day. So you can use that, but of course in the Earth it's really small. You just 1 second every 30 years. It's not a very fast way to go to the future. But you could go close to a black hole. If you go very close to a black hole, there the effect is huge. It essentially can become infinite at the frontier of the black hole. It's a very bad idea to cross the frontier of the black hole. You can't come back out. But if you get close to it, but stay away and then come out, you could stay very close to the black hole, going around the black hole for a few hours, come back out, and you would find that outside decades or maybe even centuries have gone by. So that's a way to go forward in time.
Miguel, would you repeat the question so other people can...
Oh, yeah, sorry, yeah. Well, here...
When they ask,
yeah.
go ahead, please.
Sure. I would just like to ask what your thoughts are on the many worlds theory.
My thoughts on the many worlds theory. Well, I'm not a fan of many universes. I tend to be a fan of Occam's razor, which tells you that you shouldn't multiply hypotheses when you don't need them, and I feel multiplying universes is a bit too much. So I don't really like it. I don't... That's an interpretation of quantum mechanics that I think it's not necessary at all. I think quantum mechanics is a statistical theory. It tells us what happens when you have a large number of experiments of similar systems, but it doesn't really tell you what's going to happen with one. But that's it, that you don't need any strange interpretation. I think what quantum mechanics tells us is that nature at the fundamental level is non-deterministic. It has a probabilistic aspect. So the outcome of one experiment cannot be predicted, but it has a statistical properties. You can predict the statistical outcome of many, but not of one. And I think that's all there is to quantum theory. I don't think you need to invent universes. to understand that. For you.
So, what we're saying here, to achieve warp drive, we would need something like gravity to pull us, correct?
We need something like that, yeah, distorts the geometry of
So
space-time.
when the Large Hadron Collider experiment went online, when the particles collided, they created a slight attractive force at the point of collision. If we're able to sustain that collision, we would essentially have a gravity drive.
Well, the question is if we could have essentially a gravity drive by collisions in the Large Hadron Collider, if I understand that.
Or some kind of particle collision.
Well, by particle collisions, what you do with particle collisions is you just concentrate a lot of energy in a very small region of space. That's what you do. But it's a lot of energy from the point of view of particle physics. It's a lot of energy. So these big, huge particle collisions in the Large Hadron Collider, when you collide these protons at extremely high energies, have less energy than the energy that this gets by falling into the ground. It's much less energy than that. From the point, even at that collision. The thing is, that energy in just one pair of particles is a lot of energy for two particles. But when you think of it at real everyday life scales, it's not a lot of energy.
Sure, but if you were to sustain that collision over time, then you would essentially have your collisions happening in front of your ship, whereas it would continue to pull every second.
Yeah, but it's really not a lot of energy.
There was a tabletop accelerator that was built in Texas, at the University of Texas, I believe, and it was the size that you could fit literally on a tabletop. It did require lasers to accelerate particles from an ion cloud, and that showed that the particles would actually accelerate
Yeah.
at the same energies that the Large Hadron.
Yeah, but that's different. That's an acceleration coming from electromagnetic forces, not gravity. Gravity is the weakest force of all, by far. I mean, it's orders of magnitude. It's about 40 orders of magnitude weaker than electromagnetic forces. So you get a lot of energy there, but electromagnetic energy to make it gravity. The effect in gravity is just
You have
infamous.
to wait a very long time until you can accelerate the speed.
Yeah, but the way you can see it is to produce noticeable gravitational effects, you need planets. You need the energy of a planet to produce something like gravity that we feel. So that's the measure to show you just how weak it is. Right? You need huge amounts of energy to produce gravity.
Okay, thank you.
One over there, and then
Can you explain how all that negative energy is produced by dilithium crystals? You don't need to answer.
no. Well, there was another one here.
If you were able to find some negative mass, how would you maneuver it? How would you contain it? How would you harness it?
That's a good question. I really don't know. My hope would be that you could find not so much negative mass as some kind of energy field that has the effects of negative energy, like an electric field or a magnetic field, but something much more exotic than that. But you could manipulate like you can manipulate magnetic fields. So we know how to manipulate electric and magnetic fields. So if you could find an exotic field with negative energy, but similar, you would be able to learn how to manipulate that energy field. It would be more like an energy field. Maybe this dark energy. Dark energy turns out to be a physical energy field that we can manipulate. Maybe then we could use that. But it's all speculation at this point.
Is that what that barrier is at the edge of the galaxy that the Enterprise?
That's just science fiction. Actually, in that case, bad science fiction. There's no barrier at the edge of the galaxy. You, yeah.
So I'm really fascinated by this idea of dark energy as a candidate for this negative energy for the warp drive. But one thing I'm kind of getting hung up on is that, because of the energy mass equivalence, there needs to be some mass source, if you will, or mass equivalent for dark energy. And given, Antigravity work and all of the results of that supernova experiment, we've pretty well constrained the fraction of baryonic mass in the universe. So I mean, isn't it kind of true that we don't exactly have an energy problem so much as a mass problem? We have this energy that potentially could be a candidate for
Yeah, I mean, well, the question is complicated. So she was asking if there's a source for the dark energy, and we could, so how could we have a source for the dark energy or something like this?
Yeah, I mean, like, as you were mentioning, you know, the whole idea of the proportions of energy and mass being how we can
Yeah.
theoretically change the curvature and geometry of space-time.
Yeah.
We possibly have a candidate for the energy side of that equation, but the mass is a big question mark. And so I'm just wondering if there are any theories as to what that would be.
Not really. We don't actually know what dark energy is. So actually, unfortunately, it seems that the best explanation for dark energy is that it's not an energy at all. It's just a constant. It's the cosmological constant. And that works pretty well. And I say unfortunately because if that's the explanation, then it's boring. But, the pressure hasn't changed because it's a constant. So dark energy the density and pressure of dark energy has been constant throughout the history of the universe. It doesn't dilute. That's what makes it weird. But if it's a constant, then it doesn't matter. It's just a constant. But it doesn't dilute. Matter does dilute. As the universe expands, the density of matter goes down, but the density of dark energy doesn't, which is the reason why now there's more dark energy than matter, because the density of matter has been going down. But we don't really know what the source of dark energy is. If it's an energy field, it would have been there from the beginning of the universe. It was created, who knows how, at the beginning of the universe, and just sitting there. But if it's a real energy field and it's not a constant, then it could be dynamic, and that might allow you to control it. Another possibility comes from quantum field theory, which one I like. Quantum field theory tells you that the vacuum is not actually empty. There's quantum fluctuations in all the fields in the vacuum, electromagnetic and everything field in nature is fluctuating in the vacuum. That's a problem. That's what we need a problem, because quantum fluctuations have energy. And you have quantum fluctuations in the universe of every single field. You have a huge amount of energy, in principle actually infinite, that would destroy general relativity. It would tell you that the universe couldn't exist. So it doesn't make sense. And we've known that problem forever, and we just put it on the rug. It's called the cosmological problem, constant from quantum field theory. So what people think is that maybe what happens is we don't understand quantum field theory enough, and when we do, we'll find that these energies cancel out from the different fields, and you have a lot of infinite, actually not infinites, but large quantities that cancel out, and you're left with just essentially zero or a very small value. That would be another problem, because it's a fine-tuning problem, but, but that's one of the ideas. Now, if this is true, and you have many quantum fields canceling each other in the vacuum, then if you could manipulate them and change the value of just one of them a little bit, then you would suddenly have a huge amount of energy coming from the vacuum, and that would be interesting, right? But we don't know. The thing is, quantum field theory works exactly like a cosmological constant, but the number is wrong. I don't know if you've seen it, but they call it the worst prediction in theoretical physics, because it's wrong by 120 orders of magnitude in the best case, which is great. There's another question. Well, there's one here. Yeah.
What is your idea about recent experiments on retroactive causality? Do you think it's all bogus?
Yeah, I haven't read them in any detail, to be honest, but my initial impression would be that it's bogus, yeah. Or they're not interpreting things correctly. I don't really believe them. It would take a very, very impressive things to make me believe that, but well.
See, the Sloan Digital Survey has determined that the galaxies exist in a filamentous geometry. Yeah. And if you consider the fact that the Milky Way is approximately 100,000 light years in diameter, and the Andromeda galaxy, which is approximately the same size, and is only separated by a little bit over 2 million light years, then it's only a factor of 20. So once the Milky Way gets populated with some intelligence, it's not a far step to get to the next galaxy.
Well, that's true. Yeah, that's true. The Andromeda is close by. We don't live in a very dense region of the universe as far as galaxies go. The local group of galaxies has only about 20 galaxies. Only 3 of those are big. The Milky Way is the second largest. Andromeda is the biggest, and there's another one, I don't remember its name, but it's only 3 big ones and a lot of little tiny ones. And apart from that, there's essentially nothing around here all the way to the Virgo cluster that has thousands of galaxies, but it's already about 100 million light years away. So yeah, we don't live in a very populated region of the universe. But yeah, in principle, if you could travel the whole galaxy, you could reach Andromeda not much more difficult than that. It's not that far away. And if you wait 3 billion years, we'll be here, so that's even easier. Probably you don't know that, but Andromeda is coming this way, and it's going to hit us in 3 billion years. So be ready.
I recently ran across an article which made mention of the theory called emergent gravity, which indicated that maybe there's no such thing as dark matter and dark energy. Familiar with that?
The emergent gravity, I've heard about, but I don't really know much about it. There is speculation about dark matter. I didn't talk at all about dark matter. I talk about dark energy. Dark matter is a different thing. It has normal gravity. It's just you can't see it. There's two ways to think about it. There's some form of matter that we haven't discovered that explains it, and that would be the easiest explanation. The other explanation is our theory of gravity is wrong, and you need to fix it. So both avenues of research have been looked at. Most people today, I think most astrophysicists and cosmologists today, and by most I think 98%, 99%, will tell you the first explanation is probably right. Dark matter is some form of particle we just haven't discovered in the accelerators. The other 1 or 2% will tell you gravity is wrong. But nobody's been able to come up with a new theory of gravity that explains dark matter and still explains everything else that relativity explains. That hasn't been done. So it's not that simple. There's another one there. I don't know how many questions organizers will get to tell me.
So, hopefully, this is a little quick question. You said a couple of times that wormholes, you don't know how to make them.
Yeah.
Is that similar to the negative energy problem you have?
It's even worse.
Or is it something more exotic?
It's worse because a wormhole is a change in the topology. You have something that doesn't have a hole, and then you make a hole that joins two pieces together. We have no idea how to change the topology of space-time. We don't even have a theory about that because general relativity is not a topological theory. It doesn't tell you anything about topology. It tells you about local geometry, which is a different thing. But topology, holes and things like that, doesn't tell you anything. If you give it a topology, then it can tell you if that makes sense. But how to change topology from one to another, I have no idea how to do it, not even at theoretical level. I think that's it. All right.
Not really, Miguel.
He is the quasar panoramic.
So we're going to break for lunch. I wanted to report Tiffany Frierson has arrived. Yes, she got here. Thank you.